Hello students, today we are going to start the second phase of electrochemistry where we will be discussing the conversion of electrical energy to chemical energy. Till now we have discussed the conversion of chemical energy to electrical energy by using electrochemical cell. But today onwards we will be discussing conversion of electrical energy to chemical energy. For this we need a device and that is what we call as electrolytic cell. So how can we define electrolytic cell? A device in which chemical reaction occurs by the passage of electric current. In other words, I will say in electrolytic cell electrolysis occurs. So electrolytic cell works on the phenomena of electrolysis and thus help to convert electrical energy to chemical energy. The main difference between electrolytic cell and chemical cell is that in electrochemical cell, anode is a negative and cathode is a positive pole. Whereas in case of electrolytic cell, it is just reverse. In this case, anode is a positive pole and cathode is a negative pole. Although at anode oxidation itself occurs and at cathode reduction occurs. Now before we go in detailed study of electrolytic cell, we have to clear off with some terminologies that is associated with electrolytic cell. For that, first we have to discuss what are types of conductors. There are two types of conductors, metallic conductor and electrolytic conductor. Metallic conductors are metals, for example, iron, magnesium, aluminium, silver, copper, etc. So, metal which can conduct the electricity where the carriers of what? Carriers of charge. Carriers of charge are free electrons or kernel electrons present in the metal. Whereas in case of electrolytic conductor, the charge carrier, they are ions. So I will say electrolytic conductors where the ions carry charge, we call them generally electrolyte. But the main important thing that we have to remember about electrolyte is they can conduct electricity only in molten or aqueous state, in a dissolved state. In solid state, it will not conduct the electricity. In solid state, the electrolytes will not conduct electricity because we know in solid the constituent particles are tightly packed. Then what happens in molten or aqueous state? The ions or the constituent particles, they become separate, they are free to move and therefore we say they will be able to carry current. Now when we are saying that electrolytic conductors, their charge carriers are ions, then we must know the types of electrolyte. But before that, I would like to give one example over here, like NaCl. NaCl in solid state will not conduct the electricity, but the aqueous solution of NaCl, which we also call as brine, it will be able to conduct the electricity because in that case the ions will be free to move. Now we will discuss the types of electrolytes. There are two types of electrolytes, strong electrolytes and weak electrolytes. Strong electrolytes are generally strong acid or base or salt, which is completely dissociated, or I will say alpha is 100%. Degree of dissociation is 100%. And therefore they are called as a strong electrolyte. Like HCl. HCl will completely dissociate into H plus and Cl minus, which is a strong acid. Sodium hydroxide. It will completely dissociate into sodium cation and hydroxide ion, which is a base. Sodium chloride, which is an example of salt. It will also dissociate into sodium cation and chloride anion. So these are strong electrolytes which will show complete dissociation. On the other hand, weak electrolytes are those which are either weak acid, base or salt, and they partly dissociate. They do not ionize completely in the aqueous solution. For example, acetic acid. Acetic acid is an example of weak acid that we know, and it dissociates into acetate, anion and H+. Now when we are adding water to acetic acid in the container, we will have molecules of acetic acid, will have molecules of acetate, as well as we'll have H plus ions, and therefore we will show a double headed arrow over here indicating the dissociation is not complete in this case. For one more example, ammonium hydroxide, which is a weak base, it dissociate into NH4 plus and OH minus. So in a beaker or any container in which I'll be diluting ammonium hydroxide, I will have ammonium ion, I will have hydroxide ion, as well as I will have ammonium hydroxide molecules. And therefore we say the weak electrolytes, they do not dissociate completely, they partly dissociate. Now when we know that in electrolytic cell the conductance takes place because of the presence of electrolytes. Obviously now there will be certain factors that will affect this electrolytic conductance. So now we'll discuss the factors affecting electrolytic conductance. The very first is nature of electrolyte. Just now we have discussed that if it is a strong electrolyte, complete dissociation will take place, and therefore it will carry a good amount of current, the conductance will be higher. On the other hand, the weak electrolyte, they partly dissociate and therefore less conductance. So while choosing electrolyte, we have to see whether it is a strong electrolyte or whether it is a weak electrolyte. The next factor is nature of the solvent. Now we all know that like dissolves like, the polar solute dissolve in polar solvent, and electrolytes are polar solutes. So since the electrolytes are polar solutes, obviously they will ionize to a greater extent in polar solvent, and therefore we can say if the polarity of the solvent is highest, then obviously greater will be ionization, more charges will be produced, more charges produced, greater will be the conductance. The next factor that affects the electrolytic conductance is the size of ions produced. Now when electrolytes dissolve in, or when electrolytes gets dissociated in aqueous solution, they produce ions. If the size of ions produced increases, then conductivity decreases, because as the size increases, it will hinder the free movement of the ions. Once the free movement of the ions is hindered, obviously conductivity will be hindered. The next factor is the concentration of electrolyte. Concentration to a great extent determines the conductance of electrolytic cell. As the concentration decreases means what? I will say the solution becomes more and more dilute, or dilution increases, then it will increase molar conductivity. About this we'll be studying in detail afterwards. So it's an inverse relationship. And the last factor that determines the electric conductance is the temperature. As the temperature increases, the conductivity also increases. And therefore electrolyte cells, they generally work better at higher temperatures. We need to know certain basic terms and their SI units which are very frequently used in electrolytic conductance. Now whatever things we'll be discussing under this topic, it is very important with respect to definitions as well as with respect to MCQ question, because these SI units can be asked in MCQs. Okay, so we'll begin with this. Now we know that electrolytic conductance occurs due to movement of the ions, and we will say that electrolytic conductance, it follows Ohm's law. Ohm's law we know, we have already studied in physics. What does Ohm's law says? The potential difference is directly proportional to the current. We introduce the proportionality constant. So V equals to IR, where R stands for the resistance, or I will say R equals to V by I. So what is R? R is resistance. And therefore we are going to begin with the first term, that is the resistance. We denote it as R. So what is resistance basically? It is the obstruction to the flow of the current. Resistance depends on factors like length and area of cross section. How it is dependent on these two factors? Resistance is directly proportional to the length and inversely proportional to area of cross section. We introduce the proportionality constant. So R equals to rho L by A. Rho is called as specific resistivity, that we'll be discussing later. But this is the formula that you have to remember. R equals to rho L by A, where R stands for the resistance, rho is a Newton resistivity, L is the length, and A is the area of cross section. Now what is the unit? The unit is ohm. We write it in this way. Okay. So now we'll move to the next term, that is the resistivity. It is denoted by rho. It is also known as specific resistivity. Both the terms can be used. Now from this formula, I can write rho equals to R into A upon L. So again, this is the formula based on which you will have lots of numericals. Now, if in this formula, if I take length equals to 1 centimeter and area of cross section equals to 1 centimeter square, then how does this formula changes? Then rho becomes equal to R. So how can we define resistivity? So resistivity is the resistance of a conductor of 1 centimeter length and having area of cross section 1 centimeter square. What is the unit of resistivity? It is ohm centimeter. The next terminology is conductance. It is denoted as G. What is G or conductance? It is the reciprocal of the resistance. So G equals to 1 by R. Again, this is a formula that you have to remember. Or I will say, since it's a reciprocal of resistance, and we know what is resistance? Resistance is the obstruction to the flow of current. So if it is a reciprocal, that means conductance can be defined as ease with which the current flows through conductor. Resistance is the obstruction and conductivity is the movement, easy movement of the current. The unit of conductance is Siemens. We denote it as S. Remember the definitions and MCQs, definitions and units, these are important with respect to theory as well as with respect to your theory exam, MCQ purpose questions. Now the next is conductivity. Conductivity is denoted by K. We call it as kappa. It is also called as specific conductance. So do not get confused if the question says conductivity or specific conductance. Both means one and the same thing. Now G is reciprocal of resistance. Similarly, kappa is the reciprocal of resistivity. Both are different things. So how can we define kappa? Kappa can be defined as the conductance of 1 centimeter cube of conductor. Here what is conductor? we always take electrolytic solution as the conductor. The unit of kappa is Siemens centimeter inverse or Ohm inverse centimeter inverse. The next unit is molar conductance. We also call it as molar conductivity. It is denoted by lambda, and since it is for molar, for m, for number of moles, we will write subscript as m. So lambda m is the symbol for molar conductance. Now we can define molar conductance from the name itself, conductance of 1 mole of the substance. So molar conductance is the conducting power of all ions produced by dissolving 1 mole of an electrolyte in solution. Now just before few minutes we have discussed that the conductivity, molar conductivity is inversely proportional to concentration. As the concentration increases, the conductance decreases. That means for more dilute solution, the conductance will be more. We can introduce the proportionality constant here. So lambda m equals to K upon C, where K stands for the conductivity and C stands for the conduction. Since we are discussing about the molarity, and we know in molarity we are discussing it for 1 liter of the solution, and therefore this I will multiply by 1000, and this is the formula which is very important for you people. Lambda m equals to K into 1000 upon C, where K stands for this conductivity, C stands for concentration, and lambda m stands for the molar conductance. Now let us try to derive the SI unit of molar conductance. We will substitute the units of all the quantities which are involved in the formula. So what is the unit of kappa, or what is the unit of K? Siemens centimeter inverse upon the concentration is mole per liter. But we know liter we can write as a centimeter cube also. So the unit now Siemens centimeter inverse upon mole per centimeter cube. And solving this, finally we can say that the unit of molar conductivity is Siemens centimeter square mole inverse, an important one. So these are the basic terminologies which are associated with electrolytic conductance. Generally speaking, the conductance or conductivity, how to calculate it, there are different methods available for that, and we'll be discussing that now. The conductance and conductivity of solution can be measured by 2 methods. Here is the first one, Wheatstone bridge method, which is actually experimental method. Now Wheatstone bridge you have already discussed in physics. So this is an arrangement showing Wheatstone bridge, where R1, R3 and R4 are the different resistances, and R2 is the resistance of the solution whose resistance we need to determine. So R2 will be determined in this case. It is an electrolytic solution and 2 metal electrodes are dipped in it. We know that R1 upon R2 equals to R3 upon R4. We need to calculate R2. So R2 equals to R1 R4 upon R3. So by using a Wheatstone bridge method, we can calculate the resistance of any electrolytic solution. But we have another method also. The second method for the calculation of conductance and conductivity requires all the formulas that we have discussed till now. We have seen kappa is the reciprocal of the resistivity. Here K stands for conductivity and rho stands for resistivity. Let us give it as equation number 1. Now we know rho is equal to R A upon L. So let us substitute this value. So therefore K is equal to 1 upon R into L by A. Now we know that 1 by R. This term we have already defined. 1 by R is already defined as G, which is the conductance of the cell. And therefore we can replace this term K equals to J into L by A. Now this term L by A is given another term cell constant, and that is denoted as G star. Now we have to remember that cell constant is particular for a particular conductivity cell. That means for a given cell, this G star or the cell constant will be a constant value. If you change the conductivity cell, the cell constant will also change. Now what is L in this case and what is A in this case? We know the electrolytic cell have two metal electrodes dipped in electrolytic solution. From this we'll determine L and A. L will be the distance between the two electrodes. This will be considered as L, and A L is the distance between two metal electrodes, and A is area of cross section of the electrode. So here we are defining it in a different way. Remember, cell constant will be specific for a specific cell. As the cell changes, the cell constant will also change. Now substitute in this, we'll get K equals to G into G star. Or I can say conductivity equals to conductance into cell constant. We have many numericals based on both these formulas. K equals to G upon G into G star. Conductivity equals to conductance into cell constant. Many numericals are asked not only your board exams but in your JEE exams also. So let us solve some numericals based on all the formulas that we have discussed today. Here is the first numerical. Let us write down the information given in the numerical. First of all, the concentration is given 0.001 molar. Then the resistance is given 1500 ohm. We are supposed to calculate the cell constant and the conductivity. K is given as 0.146 into 10 to power minus 3 S centimeter inverse. So it's a very straightforward numerical. We are supposed to calculate the cell constant. So G star equals to K upon G. Let us substitute the values. K 0.146 into 10 to power minus 3. But we don't have the value of G. But we know G equals to 1 by R. And therefore I can calculate it from there. So 0.146 into 10 to power minus 3 upon 1 upon 1500, and when we solve this we get the answer 0.219 cent. So this is your answer. Do not forget to write SI unit in your board exams, otherwise you will lose half mark per every SI unit. Now next is a very interesting numerical. It will involve a lot of steps. So let us begin. The very first thing, that concentration is given to us 0.05 molar. Secondly, the resistance is given 31.6 ohm. Moving on, the area of cross section is given 3.8 centimeter square, and the distance between electrodes is given, that means L is given 1.4 centimeter. We need to calculate the molar conductivity. So how do we calculate the molar conductivity? K into 1000 upon C. The value of concentration is available with me, but the value of K is not available. So for calculating K, we have to do many steps. We know K equals to 1 by rho, or I can write it as L upon R into A. Now, are these values available with me? Yes, these values are available. Length is given 1.4. The resistance is given 31.6. And the area of cross section is given 3.8 centimeter square. On solving this, we get the value of K as 0.0116 S centimeter inverse. Now, since the value of K is available with me, the value of concentration is available with me, we can directly calculate molar conductivity. So, molar conductivity is K is given 0.0116 into 1000 upon concentration is given 0.05. Let us solve this and we get the answer 232 Siemens centimeter square mole inverse. So this is the final answer. You have to remember the concepts like how to calculate K, how to calculate G, because these values may or may not be given to you directly in your question. In the next question, the electrical resistance of sodium hydroxide solution is given, diameter, length is given, and we are supposed to calculate resistivity, conductivity and molar conductivity. So there are many factors. Concentration is given 0.05 molar. Then diameter is given 1 centimeter. Length is given 50 centimeter. And the resistance is given as 5.55 into 10 to power 3 ohm. Now the area of cross section of the electrode is not available with us. And for that we need to calculate area of cross section, which we can calculate as pi r square because electrode will be spherical. So diameter is 1 centimeter. So radius will be obviously 0.5 and therefore area of cross section will be equal to 3.14 into 0.5 square, that is 0.785 centimeter square. Now we have to calculate the resistivity. Rho equals to RA upon L. The value of resistance is available, area of cross section is available with us and length is available. So let us substitute. Resistance is 5.55 into 10 to power 3 into area of cross section 0.785 upon the length is given as 50. So this comes to be 87.135 ohm centimeter. So we have calculated the resistivity. Now we are supposed to calculate the conductivity. Conductivity is K. K equals to 1 by rho. So directly I will take this value 1 upon 87.135. This comes to be 229.6 Siemens. Sorry, this is not the answer. The answer will be 1.148 into 10 to power minus 2 S centimeter inverse. So conductivity is also calculated. Now molar conductivity. Molar conductivity is K into 1000 upon C. Value of K is available. Value of C is available. So K 1.148 into 10 to power minus 2 into 1000 upon concentration is 0.05. So this value comes to be 229.6 Siemens centimeter square mole inverse. So this is how we have to apply so many concepts to solve the numericals related to electrolytic conductance. So in today's video, we have discussed the meaning of electrolytic cell, how do electrolytic cells carry the conductance, various terminology associated with electrolytic conductance. We have seen their SI units and we have solved some numericals. So based on this module, there are some assignment questions for you people. So here are certain practice questions for you people. Solve them, but remember you have to take care of the steps. Whether you want to calculate the conductance, whether you want to calculate the conductivity, 1 by R, 1 by rho, all the factors you have to consider. That's all for the day. Thanks for watching. Have a nice day.